What I want to discuss next is how do we make the RNN tractable and how do we evaluate it. So we are first going to discuss about tractability. How do we make our model more scalable? And the issue is that in a graph, in principle, any node can connect to any prior node. So this means there might be a lot of steps for edge generation, right? When node 1000 joins, we may need to generate now 1000 possible edges, right? Does it link to node 999, 998, all the way down to node, let's say, number 1, right? So this would mean that in principle we need to generate a full adjacency matrix. And this is complex and it's like and leads to very kind of long-range edge dependencies, because you have to memorize, like the model needs to memorize a lot in terms of what previous nodes were added and which previous nodes does a new node wanna connect to, right? So if you have a node ordering like I show you here, then for example, the way you would generate this graph would be add node 1, add node 2, add node 3, and only now start creating edges, right? And this doesn't feel like natural. It seems that like this, when I added node 3, I needed now to remember that 1 and 2 were already added and all that, right? And the point is that a new node needs to link to, can in principle link to any previous node, right? Even node 5 could link to node number 1. And the question is, how would we limit this complexity and how would we limit these long-range dependencies, right? Because this means that the hidden state of node 5 somehow has to remember that node 1 was added at the beginning and that 5 should link to 1. And that's a lot to kind of ask our model to do. So if we can help it in any way, that would definitely help. So the insight is that we can take because the insight is that we can come up with a node ordering that makes our model much more tractable. So the insight is that rather than having a random node ordering and having the model to worry about long-range dependencies, we are going to use a node ordering that helps the model learn better. And the node ordering we propose is called the breadth-first search node ordering. Basically, we are going to start at some random node in the graph. We are going to label it as node number 1. We are going to label its nodes as, let's say, 2 and 3, then, their neighbors as 4 and 5, right? And this leads now to a much more natural recipe to generate the graph, right? We are saying add node 1, add node 2, connect 2 to 1, add 3, connect it with 1, add 4, connect it with 2 and 3. It's kind of much more nicely interwoven, these things are. And if you say, how would you draw this graph? You'd probably draw it this way, not some other way that you first put all the nodes down and then connect them, right? So the BFS ordering, what does it buy us? It buys us the following. Because node 4 does not connect to node 1, we know that no other node is going to connect to 1 from now on, right? Because it's a breadth-first search ordering. So if, for example, node 5 were to connect to node 1, then its ID wouldn't be 5, it would be less than 5. Right? So we know that all of node 1's neighbors have already been traversed when a given node does not link to it. Therefore, node 5 and all the following nodes, right, as I said, will never connect to node 1. And why is this important? Because this means that when node 5 comes, I don't need to worry about node 1 anymore. Right? Node 1 I can kind of forget. I need to have much less memory, right? Like kind of, I don't need memory, I only need memory of 2 steps rather than memory of remembering what I did all the way at the beginning. So the BFS ordering, the key insight is that node 5 will never connect to node 1. And this means that we only need memory of 2 steps rather than the memory of n-1 steps, where n is the number of nodes in the network. And this also means that it reduces the number of possible orderings, right? Rather than considering all the possible orderings, which is n factorial of them, we only have to kind of consider the number of distinct BFS orderings, and it also reduces the number of steps for edge generation because of this insight that we know that 5 won't link to 1. And this is important because so far I explained to you, I said the edge level RNN generates the column of the adjacency matrix. But if you take this BFS-based ordering, then the edge level RNN does not really need to generate the entire column. It only needs to generate a small part of the column, because we know that the rest is 0. Right? So rather than generating connectivity to all previous nodes and having to remember all this, with the proper node ordering, we are guaranteed that all we need to do is generate just a small band of this adjacency matrix. And again, this doesn't prevent us from generating any like graphs. This is still fully general. It is just exploiting or the ability that we can renumber the nodes. We can order the nodes in whatever order we want, and because real graphs are sparse, a favorable ordering gives us a lot of benefit, because it's much easier to learn to generate just this blue part than to learn to generate this entire upper triangle of the adjacency matrix. So this was the discussion of how do we scale up our model, and its insight that we can come up, or we can decide on the node ordering, and if we are smart about it, it can really help us. It can help the model learn. The second thing I want to talk about is how do we evaluate graph generation, right? And there are two ways how you can do it. One is that we visually look at them and see whether they are similar, and that's good to get some intuition, but we also want to define a statistical notion of graph similarity. And of course you could try to say, I'll take two graphs and I'll somehow align them one on top of the other, but that is very expensive, and for big graphs you cannot do that. So you have to define some kind of statistical measure of graph similarity between two graphs. So first, let me show you some visual examples of what GraphRNN is able to do. So what I'm showing here is 3 input training graphs. These are the output graphs from GraphRNN, and here are some output from 3 traditional generative models. This is the Kronecker graphs generative model, this is the mixed membership stochastic block model, and this is the preferential attachment, the Barabasi-Albert model. And you know, what you notice is that GraphRNN, if you give it grids, it's going to generate you grids. You see a little mistakes because the model is stochastic, so it may make some little mistakes, that's okay. But you see that other models like completely fail, they're not able to generate the grid. And this is not surprising because none of these models was developed to generate grids. They were developed to generate, you know, networks with different types of properties. So that's okay, right? Like GraphRNN can generate the grid, the others cannot. What is interesting though is even if you, for example, give GraphRNN examples of graphs with 2 clusters with this kind of community structure, GraphRNN is able to learn that these graphs have that structure and it's able to generate you graphs with such a structure. While, for example, Kronecker graphs or Barabasi-Albert, they were not done to generate graphs with community structure, so they cannot do that. But mixed membership stochastic block model was developed for community structure, so it does a good job, right? And what I wanna say here is the following, right? Is that GraphRNN is super general, right? It's basically able to take these input graphs and learn about their structure and then generate new graphs with similar structure, right? You don't have to tell it, hey, I have communities, hey, this is a grid. You just give it the graph and it will figure out by itself that that the given graph is a grid and it needs to generate a grid, or that it's a community structure graph, or anything else. So it's quite remarkable that you know, such diversity of graphs the same model can cover, and you don't even have to tell it what the input graphs are. So now, how about doing more rigorous comparison about statistical similarity, right? How do we do that? Right? As I said, we cannot do direct comparison between 2 graphs, trying to do graph alignment, because graph isomorphism testing, as we have seen, is a hard problem, let's say. So the solution is to compare graph statistics. And the typical graph statistics we have already discussed would be like degree distribution, clustering coefficient, or orbit count statistics from the graphlets that I discussed, I think, in lecture number 2. So the point would be that given a graph, we are going to describe it with a set of statistics, and then we are going to say that 2 graphs are more similar if their corresponding statistics are more similar. And in our case, each of these statistics, we are going to think of it as a probability distribution. And I'm going to explain why is this important. Okay, so first is that given two statistics, maybe, two graph properties, maybe two degree sequences, two degree distributions, two orbit count distributions. We want to compare this on sets of training graphs as well as on the synthetic graphs. We want to say how similar is a set of training graphs to the set of synthetically generated graphs. And we'd like to measure the level of similarity between the two. And we are going to do a two-step approach. In the first step, we are going to do the following. We are going to take each of these graphs and we are going to describe it with a set of statistics. Like we'll say, here's the degree distribution, here's the clustering coefficient distribution. And now we'll take, and we are going to do this for all the input graphs, training graphs, as well as for all the generated graphs. And now we are going to take, let's say, degree distribution of a synthetic graph and degree distribution of a real graph. And we want to say, how much do these distributions differ? And to quantify that, we are going to use something that we call the Earth mover distance. And now that we have compared the individual statistics, now we need to aggregate and measure how, once we have a measure of degree distribution similarity, we have a measure of clustering coefficient similarities. Now we need to take these similarities and further aggregate them to get the overall similarity. And for this second level aggregation, we are going to use what is called the maximum mean discrepancy that will be based on the Earth mover distance. So let me first define the Earth mover distance and then the MMD. So the Earth mover distance kind of tries to measure similarity between two distributions or similarity between two histograms. And the way the intuition is that what is the minimum amount of effort, minimum amount of Earth, minimum amount of probability mass to move from one pile to the other so that one pile gets transformed to the other, right? So I say I have a distribution, I have two distributions, how much mass, how much of this yellow yellow Earth do I have to move between these different pillars so that I will make it and transform it into this type of distribution. So if I have distributions that are very different, then the Earth mover distance would be high, and if they are kind of similar, the Earth mover distance will be low. And Earth mover distance can be solved as an optimal flow and is found by using a linear program optimization problem, where basically say, the amount of work I have to do is, is how do I take F and transform it, how much Earth do I have to move so that it minimizes the overall cost di dj between the probability distributions x and y. So that's the intuition behind the Earth mover distance metric. And then the second part will be that we are going to use the maximum mean discrepancy, or MMD. And the idea of maximum discrepancy is to represent distances between distributions as distances between mean embeddings of their features. Right, and here I give you the formula for it, but basically the MMD between two distributions P and Q, you can think of it as that this is the if I write it in terms of some kernel K, it's the expectation over these elements X and Y that are drawn from distribution P and Q, and taking the expectation over the distribution P and Q. And of course, we need to have this kernel K. In our case, the kernel will be the L2 distance. So now let me just summarize. How do we put all this together? We are given two sets of graphs and we want to say how similar they are. The way we are going to do this is for every graph, we are going to compute its statistics. We are then going to use Earth mover distance to measure the discrepancy between the two statistics, between the two distributions. And then we are going to apply the maximum mean discrepancy to measure the similarity between these sets of statistics, where the similarity between sets elements which means the individual distributions, the individual statistics, is computed with the Earth mover distance. And this means, for example, that this way we can rigorously evaluate the correspondence between the particular set of statistics on the training graphs as well as on the testing graphs.